Hello, welcome to the Segment Routing Overview Learning Byte. I'm Gordon Mosley with the Education Services Department at Juniper Networks. I'm glad you're here. Let's get started. After successfully completing this learning byte, I hope that you will be able to understand and explain segment routing concepts. In the networking world, a way to forward traffic across a network has been around for a while, and it's called MPLS. Multi-protocol label switching. And the idea is that as traffic enters a device on your network, that device can determine that the most efficient way or your preferred way to forward that traffic across the network is by placing it inside of an MPLS label switched path, an LSP. Now to do that, the device that is going to insert the traffic into the tunnel to forward across your network will add an MPLS header right onto the traffic, and part of that header is a label, and that label will be used to initiate traffic forwarding across your network. So labels are required in a multi-protocol label switching network, right? So where do the labels come from? What do we use for labels? And traditionally in MPLS networks, we've used, I don't know if the term is correct, external protocols or additional protocols that can be used to distribute the labels. Label distribution protocol, LDP, or resource reservation protocol, RSVP, are used in MPLS networks, and they allow the devices involved to generate and distribute label information. So all the devices in the network know what labels are used to forward traffic and how to forward traffic using those labels. So these protocols have been around for a while, MPLS, RSVP, LDP, and so they're well implemented, extensively used. The issue, however, is that using these protocols to distribute the labels requires all of the routers in the segment routing domain to maintain some state. So router 1, 2, 4, and 5 in this example, if you're using LDP and RSVP to distribute labels, all those devices must maintain state information about the label switch paths that traverse it, the labels that should be used, what to do with label switch path, all that requires state information. And so we run into a scalability issue here. As the number of label switch paths increase, the state information that must be maintained is increased. So there's a pain point here that you'll reach. And the idea with segment routing is to maybe eliminate some of that state information that has to be maintained. In the segment routing world, the transit routers, let me go back a slide. I should have pointed this out. I apologize. Router 2 and router 4 in this case, see, traffic's going to come in from a site and reach router 1. Router 1 is going to determine the most efficient path is to forward traffic in a label switch path and place it in an MPLS label switch LSP tunnel. And router 2 and router 4 are just simply transit label switching routers. What we're able to do with segment routing is eliminate any MPLS state information. Router 2 and router 4 no longer have to maintain RSVP or MPLS state information. So it reduces the amount of resources that these devices have to maintain. We still need labels. It's an MPLS network, but what we're able to do, interior gateway routing protocols such as OSPF and ISIS have been extended, and so they can be used to carry additional information. Where our network example will use OSPF. In a segment routing world, the network is broken down into a series of components. The term for these components are segments. And so in an OSPF network, what do we have, right? Well, I have nodes, right? My routers that are running OSPF. Each node is assigned an ID value. It's called a segment ID or a node SID, right? And the nodes in your network, if they're running OSPF or ISIS, they establish adjacencies with their neighbors. That's how we, exchange routing information, communicate information about the locations, the routing information on our network, right? Each of the adjacencies that your nodes establish is also assigned an ID value. It's called an adjacency SID. Routing prefixes, the routing information that OSPF or ISIS has always communicated. We're going to communicate an additional piece of information about these destinations. We're going to assign a prefix ID, a prefix SID. And so with these SIDs being communicated using the routing protocols, MPLS nodes can use these segment IDs, the node SIDs, the adjacency SIDs, as labels. And so an MPLS ingress router, when it receives traffic, instead of relying on RSVP or LDP to provide it with labels to use, an MPLS ingress router can analyze its links database and figure out the adjacency SIDs and node SIDs that could be used as labels to properly forward the traffic across your network, right? Let me show you an example network I've created for this learning byte. To help you understand segment routing, I built a network. I'm showing you a network that helped me understand segment routing. See, I have access to this little small 6-node network. Please identify there's 6 nodes here because I'm going to show you this in a little bit. And what I've done in this graphic is I've outlined here for you the node SIDs that have been generated. These are VMX platforms. This is VMX1. It's an ingress label switching, router. It will take ingress traffic, place it in a label switch path that could be forwarded using segment routed adjacency SIDs and node SIDs. So the IGP OSPF in this case has been extended to communicate additional segment routing information. And now the ingress MPLS routers in this little sample network or VMX1 and VMX2 and VMX3, 4, 5, and 6 are designed to be MPLS transit routers. They just receive traffic already with labels in it and will just forward it along to the ultimate destination. But VMX1 and VMX2 will be ingress MPLS label switch paths. But the key thing is, since this is a network that has segment routing enabled, the existing routing protocol will communicate node SIDs and adjacency SIDs. You will configure a range of values in a segment routing network. There is a configuration option called a segment routing global block, and it's the numbers that will be used for the node SIDs. And you'll specify a range of numbers to be used for segment IDs, and each node will receive its own indexed value that will kind of uniquely identify it on the network. And I'm going to show you in the OSPF link state database how these node SIDs have been communicated. I tried to make this network easy to understand. VMX1 has a node SID of 101, VMX2 102, 103, 4, 5, right? Now, the adjacency SID values by default on Junos platforms in a segment routed network, when VMX5 has segment routing enabled in its OSPF configuration, it looks at its adjacencies and it automatically generates a value to use for the segment ID for this adjacency. And that's was a little hard for me initially to understand because I couldn't really figure out how things were numbered. So what I did was you're able to statically set the adjacency SIDs, and I was able to set them so they made sense to me. So for example, VMX3 and VMX1 are OSPF neighbors. They have an adjacency. And from VMX3's perspective, this interface, Gigi001, the IP address on this link is 172.22.101, and the IP address that Gigi001 uses on VMX3 to reach it, it's 101.1. And the IP address over here is 101.2. So I made the adjacency SID statically kind of to match the IP address of the device on the other side. This is VMX3's adjacency SID that would forward any MPLS frames that enter any of these interfaces with a label of 1011. He would pop the label and forward it to VMX1, if that makes any sense, right? And again, these adjacency SIDs, I statically configure them to help me understand my network better. You don't have to do that. But this is what will be used or can be used now as labels. And it's just simply enable it in your routing protocol. We don't need RSVP or LDP anymore to communicate that information. So to help you understand this better, kind of when this learning byte, you can go back and you can go forward, right? Take a look at the network. Now what I want to do is I'm going to connect to VMX1. I'm going to show you a few commands. We're going to look at VMX1's neighbors. VMX1 has 2 neighbors, VMX3 and VMX4. Here is VMX1's adjacency SID 1012 to VMX3. It has an adjacency SID of 1022 to VMX4. And we'll be able to see the node SIDs and the adjacency SIDs. We'll see them in the routing tables on the devices. We'll see them in the link state databases. And again, all of these adjacency SIDs are distributed automatically using ISIS or OSPF, and they eliminate the need for any RSVP or LDP protocols in your network, right? And so let me connect to VMX1 now, and let's look around. Okay, here is I have a secure shell connection to our VMX1 device, right? And there's a couple of commands I want to run. So I'll start with hopefully a simple one for you to see. Now, VMX2 has two OSPF neighbors, and to view the segment routing data, I'm going to run a show OSPF neighbor extensive command, right? And so let's look at this a little bit, right? So VMX1's Gigi 001 interface, it has a neighbor, and here's the IP address of that neighbor. Now here's the IP address 101.2. Now remember, I statically configured the adjacency SIDs here to kind of match that IP address to really, again, help me understand what am I seeing here. And once I knew what I was supposed to see, it helped me see, right? Now, VMX1 also has another adjacency out its Gigi 002 interface. The IP address of the device, this is VMX4. If you go back to the diagram I showed you previously, the IP address is 102.2 to reach VMX4, and so I statically set the segment routing. Another term for segment routing, by the way, is SPRING, source packet routing and networking, SPRING. So you'll hear those terms used, and I apologize, I probably should have said that earlier. It seems that segment routing is the more popular term, but you will see SPRING. But there's the adjacency SID, right? And then I could go to each device if I wanted to. Let's go to VMX3 and run a show OSPF neighbor extensive and see its adjacencies. Look at its adjacency SIDs, right? And I could kind of map that out to my network and kind of understand, right? So if, for example, VMX1 received an MPLS frame and there was at the top of the MPLS label stack was 1012, it would know to tear that label off of the stack and forward out its Gigi 001 interface to 172.20.101.2, which is VMX 3 in the diagram. So this is how this information is used. Let me show you another place. You'll see it. When I run a show route command, once this information has been communicated, it's in the OSPF, in this case, link state database. We run the shortest path first algorithm, and then we can calculate some routes. And here are our standard OSPF routes that have traditionally been stored in our IP version 4 inet.0 routing table. But when you enable MPLS, you'll have some additional routing tables that are used. For example, since VMX1 is an ingress router, there's a routing table called inet.3, and this is where traditionally label switch paths have been stored. And so in the inet3 table on VMX1, it knows how to reach router VMX2, VMX3, VMX4, VMX5, VMX6. And do you see these labels? You see this push? These are the node SIDs. So if router VMX1 wanted to forward traffic using MPLS, let's say to router 6, VMX6, it could push. It has two ways to reach it. It's learned through OSPF. It's received some labels through OSPF, and it knows exactly what MPLS label it can push onto the head of an MPLS packet and then have that packet be forwarded using the label. Any other routers in transit between VMX1 and VMX6 that received MPLS frame with 800,106 in the label would know, okay, I need to forward this to VMX6, 172.20.20. And it would be able to do that, right? We've always had the labels here in this table, but they came from RSVP or they came from LDP. This is coming purely from segment routing, right? I do have RSVP enabled. In this lab, I'm developing some information about our North Star controller, and it can provision segment routing or RSVP signal to LSPs, but I don't have to have LSP at all. These labels are coming from OSPF. And I also, in the MPLS 0 table, this is for any transit traffic, right? I might receive traffic. I'm not just an ingress router. I might receive traffic already in an LSP. And so you'll see in the MPLS.0, I always call this the label table. You know, if I receive a frame and the top of the label is 1022, my labeled OSPF route says to pop that label and forward it out this interface to this next hop, right? I can use the labels. This is how I do multi-protocol label switching. I use my label table, right? So I use one table as kind of an ingress router. What tunnels would I put traffic into? And I use my MPLS 0 as it's kind of my transit label switching router table, my label table, I call it, right? And again, these labels, all of these labels were distributed using OSPF and using segment routing. Let me show you in the OSPF database. I have a couple of commands here I say that just kind of make it a little easier. These labels, remember OSPF, we use the opaque LSA, LS link state advertisements to communicate this additional information. So I'm going to just run a show OSPF database command. It's the opaque area link state advertisement. So I'm kind of doing a filter here with this pipe find. And so in opaque area, in this opaque LSA, we're using segment routing, right? And what we're just communicating here is the range of labels that can be used to generate node SIDs. I used 800,000, and this is the start of what's called my segment routing global block. This segment routing global block is a series of numbers that can be used to generate the node SIDs. And you want all of the routers in your segment routing domain to use the same value. So we all know what the range of labels can be. This will help you maintain your sanity. And I've created a range of 4,000 labels available to identify my nodes. Each one of them can get a SID between 800,000 and 800,300 or 803,999 or something like that, right? 4,000 labels. That's enough. I only have 6 nodes, right? And this came from router 1. This is router 1's LSA. This is from VMX2. This is from VMX3. And so I can kind of verify that every node in my network is kind of using the same label range. And that's good. I like that, right? Let's keep going. So I'll see 6 of those, one from router VMX1 all the way through, router VMX6. Now I'll see in this opaque area, here's VMX1 again. And this is VMX1 specifying its node SID index value. You see, we take the base label. Every node says, well, the base labels are 800,000. Every node, we saw 1 through 6, knows that. And here's VMX1's individual node SID. So actually, the complete node SID for VMX1 would be 800,101. And the complete node SID for VMX2 would be 800,102. So everybody uses the same block, 800,000. There's 4,000 labels available, and then you'll configure each node to have its own unique index value. Each node's index value is distributed using OSPF in this case. Every node knows the label range. Every node knows everybody else's index value. And so every node can calculate every node SID in the domain. Isn't that cool? And we didn't need RSVP or LDP to do that, right? Let's keep going. This is so much fun, and I want to kind of get down to show you. So there's, VMX5's, 105. VMX6 would be 106, would be its node SID. And then here are actually the adjacency SIDs. They're also communicated using these opaque area link state advertisements. And here's from VMX1, right? It has 2 adjacencies, right? Out this particular, link, it communicate with VMX4. Here is the label assigned to that adjacency. Right, here's the adjacency that it has, with a different device. So these adjacency SIDs And the node SIDs are communicated using the existing routing protocols that exist in your network. And these SIDs can be used by MPLS routers as labels. Let's replace RSVP. Let's replace LDP. And that way we don't need to maintain the state information for those protocols on the transit routers in our network. And that's the advantage. So the idea with segment routing, break your network down into components or segments, nodes, and adjacencies. Give each of those ID values. Allow the routing protocols, your ISIS or your OSPF, interior routing protocol, to communicate those ID values. And then simply use those ID values as labels. Right? That's the idea of segment routing. In this Learning Byte, we explained segment routing concepts. Thank you very much.
Visit the Juniper Education Services website to learn more about courses. View our full range of classroom, online, and e-learning courses. Learning paths, industry segment and technology-specific training paths. Juniper Networks Certification Program, the ultimate demonstration of your competence. And the training community, from forums to social media. Join the discussion.